Hello, I am Dr. Ramesh Chand. I am going to discuss about pinch effect and instabilities in plasma. As we have seen in previous video that the mechanical pressure P and the magnetic pressure B square upon 2 mu 0 are related by this relation. This shows that apart from gravitational effect, any change in mechanical pressure P must be balanced by an opposite change in magnetic pressure. If the fluid, here it is plasma fluid, is confined within a certain region so that P falls rapidly to zero, outside that region the magnetic pressure must rise equally rapidly in order to confine the fluid. This is the principle of pinch effect. That is to say that confinement of plasma or conducting fluid by self-magnetic fields is called pinch effect. For example, if we take an infinitely long cylinder of radius r with current density J and magnetic field B, then the average pressure inside the cylinder must be equal to mu 0 upon 8 pi square I square upon r square or B square upon 2 mu 0. Now let us discuss about instabilities. If we look only at the motions of individual particles, it would be easy to design a magnetic field which will confine a collisionless plasma. We need only make sure that the lines of force do not hit the vacuum wall and arrange the symmetry of the system in such a way that all the particles, drifts and so forth are parallel to the walls. From a macroscopic flood viewpoint, however, it is not easy to see whether a plasma will be confined in a magnetic field designed to contain individual particles. No matter how the external fields are arranged, the plasma can generate internal fields which affects its motion. For instance, charge bunching can create electric field which can cause E cross B drift to the wall. Currents in the plasma can generate magnetic fields which cause gradient B drifts outwards. The difference between equilibrium and stability in a mechanic in a plasma is best illustrated by the example given here. An equilibrium is a state in which all the forces are balanced so that a time independent solution is possible. We consider in the figure a marble resting on a hard surface in these examples. The equilibrium is stable or unstable according to whether small perturbations are dumped or amplified. Are damped or amplified. In this case, you see the marble or the ball is in a stable equilibrium as long as it is not pushed too far. Once it is moved beyond a threshold, you see threshold is this. It is an unstable state. This is called an ex- explosive instability. In this case, the marble or ball is in an unstable state, but it cannot make very large excursion. Such an instability is not very dangerous if the nonlinear limit to the amplitude of the motion is small. The situation with the plasma is of course much more complicated than what is seen in these examples. To achieve equilibrium requires balancing the forces on each fluid element of the two problems, equilibrium and stability. The latter is easier to treat. One can linearize the equation of motion for small deviation from an equilibrium state. We then have linear equations just as in the case of plasma waves. The equilibrium problem, on the other hand, is a non-linear problem like that of diffusion. In complex magnetic geometries, the calculation of equilibrium is a tedious process. The treatment of plasma waves, we assumed an unperturbed state which was one of perfect thermodynamic equilibrium. The particles had Maxwellian velocity distributions and the density and magnetic field were uniform. In such a state of highest entropy, there is no free energy available to excite waves, and we had to consider waves that were excited by external means. We now consider states that are not in perfect thermodynamic equilibrium, although they are in equilibrium in the sense that all forces are in balance and a time independent solution is possible. The free energy which is available can cause waves to be self-excited. The equilibrium is then an unstable one, and instability is always a motion which decreases the free energy and brings the plasma closer to true thermodynamic equilibrium. Instabilities may be classified according to the type of free energy available to drive them. There are four. main categories. First one is streaming instability. In this case, either a beam of energetic particles travels through the plasma or a current is driven through the plasma so that the different species have drifts relative to one another. The drift energy is used to excite waves and oscillation energy is gained at the expense of the drift energy in the unperturbed state. The second is the Rayleigh-Taylor instability. In this case, the plasma has a density gradient or a sharp boundary so that it is not uniform. In addition, an external non-electromagnetic force is applied to the plasma. It is this force which drives the instability. The third one is universal instability. Even when there are no obvious driving forces such as an electric or a gravitational field, a plasma is not in perfect thermodynamic equilibrium as long as it is confined. The plasma pressure tends to make the plasma expand, and the expansion energy can drive an instability. This type of free energy is always present in any finite plasma, and the resulting waves are called universal instabilities. The fourth and the last one is kinetic instability. In flat theory, the velocity distribution are assumed to be Maxwellian. If the distribution are in fact not Maxwellian, there is a deviation from thermodynamic equilibrium, and instabilities can be derived by the anisotropy of the velocity distribution. For instance, if T1, T parallel or T perpendicular, that is the temperature of the parallel moving species, and T perpendicular, that is the perpendicular moving species temperature, are different, and an instability called the modified Harris instability can arise. In mirror devices, there is a deficit of particles with large V parallel upon V perpendicular because of the loss cone. This anisotropy gives rise to a loss cone instability. Not all instabilities are equally dangerous for plasma confinement. So, we are considering here the different type of instabilities in plasma, and I am going to stop this video at this point. Thank you.